The Wonders of Waves, brought to you by Carl. So I went surfing today.
Oh yeah?
Yeah. Huh. Waves are really gnarly.
Yeah, they were pretty sick where I was too.
Yeah. Water's a little cold though.
Yeah, I was thinking about totally investing in a wetsuit.
See, they're a little constricting for me.
For sure. And there was a lot of drama on the beach today though.
Really?
Oh yeah. This dude would totally aggro on this cook that dropped in on him. It was hilarious. You should have been there.
I knew I should have gone bird walk today. Huh. You know what I've always wondered?
Huh.
What exactly is a wave?
I've always pondered that question myself. I wonder who we could ask.
Cam!
Hi guys, I'm Cam Nye, if you haven't noticed.
I thought it was Bill Nye.
Well, I'm his cousin.
Oh, okay.
Well, I'm here to explain your question about waves.
So, what exactly is a wave?
Well, I'm going to explain that, and we're going to start out with a definition.
Okay.
A wave can be defined as a disturbance that travels through a medium from one location to another. A wave can be considered to be an energy transfer phenomenon. As the disturbance travels through, the energy is displaced from one place to another. So,
yeah, so I don't get it.
I don't get it either.
well, that's fine. Let's go to the lab, and Lauren, my colleague, will help explain the anatomy of a wave.
Okay.
Hey guys, I'm Lauren, I'm Cam's assistant, and I will tell you some properties about a wave. First we have the amplitude, and that's how big your wave will be. Next we have the wavelength, which is also called the period, and that is one point of the peak on a wave to the same point on the next wave. And that's how close your sets will be together.
Gotcha.
And a frequency is the amount of waves that pass through a certain point in a certain amount of time. And that's how many waves you'll have in a set.
All
right, let's go to the equation board and look at some equations. All right, here's our equation for frequency, which is 1 over t, or time. And to find time, you take two consecutive waves and you measure the distance in between a certain point on each wave, the exact same point. So you take this time and you divide it, or 1 divided by that amount. So for example, you have 20 waves in 10 seconds. So your t would equal 10 divided by 20, which equals 0.5. So you take 0.5 and you plug it in for time. So 1 divided by 0.5 equals your frequency. And also, we have another equation for frequency, which would be velocity divided by the wavelength. So you can also rearrange these equations. If you have any of the two variables, you can solve for the third.
That was a great demonstration of the anatomy of a wave and the equations of a wave. This also sets us up for a great experiment. Let's go find velocity at the Birch Aquarium, where Dia and Renee are going to go and find the velocity. Let's go.
Hey Cam, hi. I'm Lauren. We're here at Birch Aquarium at Scoop Institute of Oceanography, and we're going to go in and look at their wave simulators. So let's get going. Hey, we're here at Birch Aquarium, and we are using their wave simulator, and we're going to find the wavelength and the frequency of the waves. So to figure out the wavelength, we have to measure the peak from one wave to the other. So we brought a measuring tape, and we're going to measure from this peak right here to right here, and we get 82.5 centimeters. We're going to use
This is a stopwatch that they provided with us on their display, and we're going to measure the frequency of the waves by counting the number of times it passes the line in 30 seconds. So here we go. Ready, set.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26.
Okay, that's it. So 26 times in 30 seconds. Now we'll go back to the lab and use these measurements and calculate the velocity.
Okay, here we are at the lab, and we're waiting to find out what velocity is. So, Dia Renee went to Scripps Aquarium, and they should be bringing us our data soon.
Hey guys.
Hey.
I'm here bringing the data. Dia's still over at Birch Aquarium doing some other research, so let me write it down for you. Okay, we found the frequency to be 26 waves for 30 seconds. And we found the frequency, or the wavelength, to be 82.5 centimeters. All right, I hope you can use that information. Good luck.
Thanks, Renee.
Bye.
Okay, so now that we have the data, how are we going to solve this problem?
Well, we have our wavelength right here, 82.5 centimeters, but our frequency, it doesn't look the same as this.
Okay, so here's why this looks different. Let's solve it over here. So T is actually going to be equal to the opposite, well, the inverse of this. So let's actually put it under the entire equation. So F equals 1 over, and we're just going to flip these. So it's 30 seconds over 26 waves. Okay, so looking at this, this should be about 0.87 seconds inverse. But you can't always just trust yourself, so that's why I carry a calculator. So let's do this on the calculator real fast. And that's exactly what it is. It's 0.8666. So now that we have this for frequency, so do you understand this now?
Yes.
Okay, good. So what's the next step?
We have our wavelength, but it's in centimeters. I thought it was supposed to be in meters.
It does. In order to solve this problem, we're definitely going to have to put it in meters. So the step here is what we're going to do is 0.82.5 centimeters, and we're just going to divide it by 100. And that's going to equal 0.825 meters. Okay, so now we should be able to just plug it in. Okay.
All right. And that equals?
About, I think it's 0.72. But again, never depend too much on your calculator. So it's 0.82, and yep, it's 0.72 meters per second. And there it is, problem solved. The waves travel 0.72 meters per second.
Totally get it. It's just how fast the waves are moving every second.
So I got a question. I'm thinking about entering like a big wave surfing contest, and I really want to know, how do I make bigger waves? Because I just want to be like, whoa, pedal!
We should get back to the board. Let's talk about that issue on how waves get larger and smaller. Now, as you can see, there's two waves here, and they go up at the same time and go down at the same time. And this is called in phase, also known as constructed. this is how waves get larger, and they build on each other. So, but on the other hand, you have waves where they go up and down at the same time, and then down and up at the same time, which means it's out of phase. And they're basically going to cancel each other out, making a destructive wave. And this is what you want to avoid. So here we have a diagram and the beach, and Lauren's going to explain how it works.
All right, here we have 2 points in the ocean where waves start or are formed. And these lines represent waves, and these black dots are where you have constructive interference. So here you'll have the waves meeting together at the same point, creating a big wave. And then your deconstructive interference will be in the middle of these points. So right after you have your constructive interference, right in the middle, between these two constructive interference points, you'll have your destructive, where you'll have no wave at all.
Okay, so now you see what you need to avoid, and now you can see where you can find the big waves. This is actually going to be the largest wave right here, because the two waves right here actually meet and make the largest wave. So that's probably where you want to be. Now, let's go back to Dia at Birch Aquarium, and let's go see how this issue works on a global scale.
Hey guys, we're here at Birch Aquarium again, and we're going to demonstrate how waves interfere with each other. To do this, we're going to use this animation, and we're going to take a look at a tsunami. Now, as you watch the world spin around, it's going to stop in the area where tsunamis usually occur. As you can see, the interference is some waves are growing and some waves are disappearing. This is constructive and destructive interference.
Here for that global demonstration about how waves actually work and interfere with each other. But does all this actually answer your question about how waves work?
Yeah, I think it really does. Does all this stuff apply to sound and light waves too?
Yeah, actually.
Remember in our quantum theory class, we learned about this photoelectric effect. Light actually travels in particles.
That's right, I totally learned that last week.
Yeah. So, surf session? Totally.
Cam
Brought to you by Cameron Nisus, Karen Schoenberg, Andrea Thornquist, Renee Carlton, Laura Piper, and Lauren Gambetta. Hey, wait a second, that spells Carl. I just wanted to say a special thanks to Birch Aquarium at Scripps Institution of Oceanography.
I'm going to start out with a definition. A wave can be defined as a media.
Oh my. Do you divide it? Or is it, check out.
Yeah, hey Cam 9, aren't you supposed to divide it?
Calculator, use your calculator.
Oh.
No way!
Woo! Static electricity.
Oh, looks nice it's not playing.
Why not?
Screw it, I don't know, it just wasn't.
Science guy!
It's all about Bill. It's all about Bill.
We love you, Cam 9! Say bye, guys.
Ciao. Bye. Au revoir.